Welcome to The Explainer. So today we are going to completely demystify algebra. We're going to frame it not as some complex web of arbitrary rules that are just meant to confuse you, but actually as a straightforward, highly logical, secret language, and we're going to decode it together. Think of it a bit like learning to read sheet music. At first, it's just, dots and lines on a page. But once you know the rules, you can play an entire symphony. Okay, let's dive right in.
Here's our roadmap for the day. We'll start by decoding the alphabet, move into simplifying in like terms, tackle expanding brackets, cover substitution, and then finally look at its real-world power. We're moving step by step to keep this completely anxiety-free.
All right, Section 1, decoding the algebraic alphabet. Because to become a master cryptographer, we obviously first need to understand the basic letters and symbols of our new language.
Now, the core definition of algebra is honestly beautifully simple. It's really just a language that uses letters and symbols to represent numbers and their relationships. So you see things like x plus 5 or 3a minus 2. Those letters, the x, y, a, or n, we call those variables, literally because their values have the ability to vary or change. They're just elegant placeholders for the unknown. Like, imagine you're grabbing coffees for your friends, but you aren't sure how many you need yet. That unknown quantity, that's your variable.
To read this language fluently, think of these definitions as your ultimate decoder ring. We've got our variables, like x. We have constants, which are fixed numbers like 5, that literally never change. Then we have coefficients. These are the numbers multiplying a variable. So in 3x, 3 is our coefficient, telling us we have 3 of that unknown quantity. But look at how these smaller pieces build up. A term is like a single word in our language, 2x, or just a standalone 5. An expression is more like a phrase, combining terms into 2x plus 5. And then finally, an equation is a complete sentence showing equality, like 2x plus 5 equals 11. You can literally read it out loud like a sentence telling a story.
Let's actually see this vocabulary in action with the expression 4x plus 7 minus 2y. If we break this down into its individual pieces, our terms are 4x, 7, and negative 2y. Notice how 4 and negative 2 are our coefficients. They are firmly attached to those variables, x and y, scaling them up or down. Meanwhile, that 7 is just standing entirely alone as a constant term. It's fixed. It isn't influenced by any variable at all. It's always just going to be 7.
Moving on to Section 2, simplifying and like terms. Now that we have our fundamental words down, let's look at the grammar rules for grouping them together.
To simplify algebraic sentences, we absolutely must distinguish between what we can and cannot combine. So 3x and 7x, those are like terms. 5a squared and negative 2a squared, also like terms. But x and x squared are not like terms. Neither are 3a and 3b. The golden rule you have to remember here is that like terms must have the exact same variable raised to the exact same power. Otherwise, trying to combine them is literally like trying to shove a square peg into a round hole. It just doesn't work. I mean, you can add 3 apples and 7 apples to get 10 apples, but you can't add 3 apples and 3 bananas to get 6 apple bananas, right? They have to match perfectly.
When we apply this rule to simplify expressions, it's really all about efficiency. It's exactly like grouping those apples with apples to make everything cleaner to read. In our first example, 3x plus 5x easily becomes 8x. In the second, slightly longer one, 4a plus 2 minus 3a plus 7, we logically group the a's together. So 4a minus 3a gives us a. And we group the constants together. So 2 plus 7 gives us 9. Our final simplified, elegant phrase is just a plus 9. We took a cluttered phrase and made it super crisp and direct.
But listen, here is a major pitfall you've got to avoid: combining unlike terms. You might look at 3x plus 4 and really want to write 7x. Absolutely not. That 4 does not have an x. You cannot merge a variable term with a constant. It's kind of like having 3 mystery boxes and 4 loose items, and then claiming you have 7 mystery boxes. It's just not true. 3x plus 4 cannot be combined. It stays exactly as it is. Always remember, numbers and variables need matching identities to be added together. All right, Section 3, expanding brackets. Next up, we encounter brackets in our language, which we need to skillfully unpack using a little something called the distributive property.
Expanding brackets is a highly logical two-step procedure. Step 1, multiply the outside number by the very first inside term. Step 2, multiply that same outside number by the second inside term.
It's called the distributive property because, well, you are literally distributing the value on the outside to absolutely everything trapped on the inside of those brackets. It's just a fair and equal mathematical distribution.
Let's see how beautifully this actually unfolds with a real example. We have 3 times the bracket of x plus 4. Following our logic, we distribute that 3. 3 times our first term, x, gives us 3x. Then we distribute the 3 to our second term, 4. 3 times 4 gives us 12. So our unpacked, fully expanded phrase is cleanly written as 3x plus 12. It really is that straightforward. You just have to be methodical about it.
Now, a super common trap right here is forgetting to distribute fully. It is so easy to write 2 times the bracket of x plus 5 as just 2x plus 5. Do you see what happened there? The 2 was never distributed to the 5. The 5 just stayed a 5. The correct way is to make absolutely sure that outside 2 hits every single term inside. 2 times x is 2x, and 2 times 5 is 10, giving us 2x plus 10. You can never forget to multiply that outside number by the second term. Oh, and quick pro tip, always watch your negative signs during this process. They will absolutely sneak up on you.
Moving right along to Section 4, Substitution and Formula. We've mastered the grammar of expanding and simplifying, so now it's time for translation. This is where we substitute numbers back into our letters to get real, tangible results. Substitution is really where algebra starts to feel a bit like magic. Say we're asked to find the value of 2x plus 3 when x equals 4. All we do is carefully swap out our variable x for the number 4. Our expression becomes 2 times 4 plus 3. 2 times 4 is 8, plus 3 is 11. Just by replacing that one variable, our abstract algebraic phrase instantly translates into a clear, concrete value of 11. The unknown suddenly becomes perfectly known. And this brilliantly illustrates exactly why substitution is so powerful. It brings us straight to evaluating formula. A formula just shows a relationship between different quantities. Take the area of a rectangle, for instance. Area equals length times width, or A equals L times W. If we substitute a length of 6 and a width of 4 into our formula, we get an area of 6 times 4, which equals 24. We literally just used our algebraic language to calculate a physical space. Which naturally leads us to our final section, Section 5, Real-World Algebraic Power. Now, you might be sitting there wondering why we go through all this trouble to decode this language in the first place. The answer lies in its massive, massive real-world application. Think back to that number 24 we just calculated. We have to pause and ask ourselves, 24 what exactly? It could be 24 square units of a blueprint for a house you're building, or it could be the precise dimensions of a microscopic pathway on a silicon chip you're designing. The variable nature of algebra means it scales perfectly to fit whatever problem you're trying to solve, no matter how massive or how incredibly microscopic it is. This hidden code is literally the invisible infrastructure of our entire modern world. Physics, computer programming, finance, engineering, AI, data science. This exact language, the letters, the brackets, the simplifying rules we just walked through, it forms the absolute foundation for all of it. From writing complex computer software to calculating the structural integrity of suspension bridges to managing global financial systems. Algebra is the architecture running behind the scenes of our lives. Which brings us to our final stop. You've now unlocked the foundational building blocks of algebra. You understand the grammar, the syntax, and the incredible real-world power of this invisible code. It is an essential skill for navigating our incredibly data-driven world. So the only provocative thought left for you to ponder today is this. Now that you know the language, what will you decode next? Thanks for joining me on this explainer, and I'll catch you next time.